All right, everyone. Welcome to another Infrageometry life science stream. Today we're going to be reviewing some of the recent advancements that we've made in the front of weighted derivations. As many of you might remember, we identified these so-called weighted derivations, which are a generalization of the ordinary notion of derivation in the context of finite, discrete sort of whole step analogs of vector fields or differences in a manifold. So I think Uti can walk us through one of his very exciting findings. One of the open problems and one of the main questions that we've had since the very beginning has been whether weighted derivations, at least in its purely algebraic formulation, carry a natural internal operation, so that when some endomorphisms satisfy the weighted derivation property, they can be combined with some of the primitive operations, such as pointwise addition, pointwise multiplication, or composition, as indeed one can combine any endomorphisms, so that they still retain that weighted derivation property, which is, as you might remember, the generalization of the Leibniz identity with an extra term that has sort of a quadratic term in the derivative. So maybe Uti, if you're happy and ready, you can please go ahead.
Oh, I can present my screen and write on it as I did last time.
Yes.
Yeah, so I assume you guys can see my screen.
Yes, that's good.
Okay. So there have been like a lot of developments, one of which, as Carlos mentioned, is the operation under which derivations are closed. And also there have been like even more developments, and what I have found in general is that there's a nice correspondence between like theorems of derivations and theorems of weighted derivations, and a lot of the same properties hold. So I think first the best thing to do is to review all the findings and then discuss what's next. Does that sound good?
That sounds great.
Okay. So first, if you remember from the last live stream, we proved that if W is in K, any element in the field, and phi is an algebra homomorphism, then phi minus the identity is a weighted derivation. Of weight 1. And this can easily be proved. I will not do it here because it would take some time, but it's quite easy to see and can be worked out. So this is for W is equal to 1, but it turns out that if I just put a 1 over W sign over here, then this is a derivation of weight W. And so now the question to ask is, are all weighted derivations of this form? And so then there's another theorem that can easily be shown. It's purely computational, that let A be a K algebra, and assume let F be a weighted derivation of weight W. So this is the notation I'm using. Then we can show that W times F, where I scale in the endomorphism by the element in the field, plus the identity, is an algebra homomorphism. So this immediately tells us that all of the derivations must be of this form, because if I have like is an algebra homomorphism. So if I have an algebra homomorphism phi, I know that I can do this and get I can create a bijection essentially. Let's call that psi from the set of algebra homomorphisms to, let's say, the set of weighted derivations of weight W that takes phi and gives me this. And this is a bijection because the inverse map exists as well, which takes an F and maps it to W F plus the identity. And it's easy to see that if I compose psi with psi inverse, I get the identity and the same thing on the other side. So I'm just equating this to F, and that's how I got this. Right? I put when W went over there, and then the identity went over here. Carlos, is that clear to now?
Yeah, that sounds good.
So I mean, it's pretty obvious that all derivations take this nice form. And so one immediate thought over here is that we know that a derivation, a W derivation.
So one comment at this point would be that that's all for non-zero derivations.
Yes.
Right.
If you have a non-zero algebra homomorphism,
it
produces.
But
sorry, if you have the identity algebra homomorphism, then you get the zero derivation, which is trivially like a W derivation for all W.
Yes, the zero derivation is a W derivation for any W, but zero derivations, not the zero derivations, but derivations of weight zero, they are not included in this.
Yes, they are not included, precisely, which are essentially like normal derivations. They are not included here. So for all W non-zero.
Okay,
and that's the point I was basically coming to right now, is that, so we see that there's a correspondence between algebra homomorphisms and W derivations, and we get a normal derivation if I take the limit of W1 to 0, right? And so this tells me something, right? This tells me that maybe there is a 1-1 correspondence between algebra homomorphisms and normal derivations, where given an algebra homomorphism, I can create essentially a class of W derivations given by this. And then I take W to go to 0, right? Mm-hmm. So I know that each of these must be W derivations. And as I take W to go to 0, each of these satisfy the normal derivation property more and more closely, because the W term goes to 0 and so it becomes less. And so the way to kind of see this is that, like, this is essentially like this form, right? Like this is something that looks like this.
Yep.
And so this, we take epsilon to go to 0 and W go to 0. So this is telling us that maybe there is a way of taking an algebra homomorphism and getting straight to a derivation, right? Now, in the literal sense, if I take W to go to 0 and let's say our field has a nice analytic properties, then this would go like, this goes to infinity, essentially, this homomorphism, because 1 over W goes to infinity. Mm-hmm. So it's not like the most straightforward thing we can do, because W is in the denominator. And so it turns out that I was actually just working this out before the live stream. That if you guys remember, when we looked at the polynomial ring Kx, over there, the set of all derivations is, so A is equal to Kx, is essentially of this form. Now, we also know that the set of all algebra homomorphisms are in bijective correspondence between Kx as well, because Kx is generated by one element. And so the algebra homomorphism is completely determined by the element, like what x is sent to. So if x is sent to P of x, then xi is sent to P of xi. And since an algebra homomorphism is also linear, sorry, it's P of x to the I, then any linear combination, and this essentially spans all elements inside Kx, this must be mapped to, and so it's completely determined by what the generator is into. And so this like conjecture that we made, that the set of derivations must be in 1-1 correspondence with the algebra homomorphisms, holds true in K of x, and it also holds true in K of xy, and so on. Because of K of xy, the set of all derivations are determined by two polynomials, P of xy and K of xy. So it's of the form P of xy partial x plus q of xy partial y. And so this correspondence seems to hold true in all the normal cases. And so that's the next thing I was trying to do after this. And then I found, just before the live stream actually, that in this specific example of k of x, there is a nice way to take a derivation, take an algebra homomorphism, get a derivation. And that is, take the algebra homomorphism phi, and then construct, and then we know that the w derivations are of this form. Construct a new algebra homomorphism that takes x to x plus phi of x times w. And then if I take the limit as w goes to 0 of, just when the live stream started, someone else entered. Before that, no one else entered. And if I take the limit as w goes to 0 of phi minus the identity times any element q, it gives me the derivation that corresponds to phi. So okay, so it's a bit hard to explain, but I haven't formalized this yet, that how would we actually take maps that go from an algebra homomorphism to a derivation. But that's the next step that I have to do. Carlos, do you have any comments?
Yeah, so one comment here is, in the kx case, the correspondence is as you described last time, right? So we actually have a bijection because of the one-dimensionality of derivations in that context. Is that right?
Yes, but it also holds true in k of xy, because yeah, sorry for the disturbance.
No problem.
So it also holds for k of xy, because we know that the set of all derivations of kxy to k of xy is essentially p of xy d by dx plus q of xy d by dy. So that p and q are inside k of xy. So essentially this is in correspondence with k of xy cross k of xy. You need two polynomials to determine any derivation. And also this holds true, and also this is in 1-1 correspondence between a set of algebra homomorphisms, because it has two generators. And so we only need to decide what x is sent to and what y is sent to. So x will be sent to, let's say, some polynomial p of xy, and q of x is sent to some polynomial q of xy, then this determines an algebra homomorphism completely from k of xy to k of xy.
So but there's something I'm not following here, at least. So you're saying there's a one-to-one correspondence between derivations of xy polynomials and algebra homomorphisms?
Yes.
Of the ring of two polynomials?
Yes, because an algebra homomorphism also has to be multiplicative, right? It's not just a linear map. And so any polynomial in k of x, y has two generators, x and y. So it's of this form. These are all the polynomials, right? In k of x, y. You can write any element of k of x, y in this form.
Yep.
And so so let's say I have an algebra homomorphism phi, and let's just assume that I have an algebra homomorphism phi. It will send this. Since it is linear, it will not change the aij's, and since And so phi of xi, it being an algebra homomorphism, must be this, right? Because it's x times x times x I times. And so it should be this. And similarly, it should be this. And so if I know phi of x and phi of x and phi of y, I know the entire algebra homomorphism. And the other way around as well. Like it obeys a universal property that if you have an algebra generated by n generators, then if I have a set map from those n generators to n things in the algebra, then the diagram commutes, right? So, and in case of derivations, it is actually not entirely clear at all from the start that we'll get these two polynomials. I think the derivation is okay. That was the pun. The derivation of the set of all derivations is a bit confusing and non-trivial. But over here, we see that there's a correspondence, and I feel like the W derivations can help us go from an algebra homomorphism to a derivation.
I mean, what I'm failing to see is the correspondence between homomorphisms and derivations of the xy polynomials.
Okay. So do you agree with me that the set of all algebra homomorphisms from K of xy to K of xy is in bijective correspondence to K of xy cross K of xy? If you agree with this, then it's okay, because I need to decide what x is sent to, so that's the first element, and then I need to decide what y is sent to, that's the second element, right? So this is a bijection. And similarly, we know, like this is an established mathematical fact, that the set of all derivations from the polynomial ring of two variables over a field K. The field is necessary. This does not hold true in like arbitrary things. Is of this form. So this is also in bijective correspondence with this. And so, since they are in bijective correspondence with the same set, they must be bijectively. This is determined by two polynomials, and this set is also determined by two polynomials. It's like every element of this set is determined by two polynomials, and so is this set.
Yeah. No, I understand that. I think I think I had this question last time for kx and still stands for kxy, which is how does the algebra? I mean, these are bijections. I can see that, but yes. How does the algebra map through these bijections? So, because I mean, the derivations are interesting not because they are maps, but because they are derivations, right?
Yes.
Similarly with homomorphisms, they are interesting not because they are maps, but because they are algebra homomorphisms.
Yes.
So, I mean, what happens to that? I mean, to me, this is a very counterintuitive statement. I mean, it's true that these are multiplicative. So in the geometric picture, the multiplicative morphisms of functions, which is the analog of the polynomials here, you don't usually deal with the entire family of those. You deal with the subset of, say, pullback by differentiable maps, right? So those induce multiplicative morphisms. So they are linear and multiplicative. So it seems strange that if I give you I mean, let me just translate in my head what this statement seems to be saying, which is that if I give you some functions on smooth functions on R2, right? I define the derivations over R2, right? So this is some, Lie algebra, not finitely generated infinite dimensional Lie algebra, and then you have some functions, some diffeomorphisms, if you want, on R2, and those can pull back or push forward the functions of R2, right? So, and those are, by construction, multiplicative, right? So they give you algebra homomorphisms, right, of your commutative algebra of functions. So this result will be stating something like, I give you one of these diffeomorphisms, and then I can immediately produce a single vector field, a derivation on the plane. That seems to be off. Something is not quite matching here.
I'm not familiar with the geometric picture, but okay, so here's what is, I agree it's not the most intuitive result, but here's what is non-intuitive about this result for me, is that this makes sense because it's generated by two elements. This is not like, I won't say that this makes sense or it does not make sense. Like, if someone told me and I had no knowledge of, like, how would this be proved, then it's hard for me to just say that, these must be the set of all their derivations. Because if I see the partial derivatives, then I can be like, oh, you know what, it makes sense. These are like independent and it can span directional derivatives in like any direction and so on. But purely algebraically speaking, if I just knew that the set of derivations satisfy the Leibniz rule, then it would be hard for me to say that it's in 1-1 correspondence between algebra homomorphisms. It's like, I don't know how anyone would come up with this. But the reason I think this is definitely... Yeah, you were saying?
No. I thought you were going to say something else. Yeah, go ahead.
So now we've established that every W derivation is of this form. And if I take the limit as W goes to 0, this map continuously behaves
like a derivation.
Like more and more closely.
I think that
since each...
there's something missing there because, that is going to be literally true and matching all our intuitions when you replace phi, some constant phi, some fixed phi, with phi sub W, which is a...
Yes, precisely.
Yeah.
Yes, and so that's what the functorial correspondence is. If I just say that W goes to infinity, then this map becomes like the trivial infinity. Like, it doesn't do anything. Like, it just blows up to infinity. That's boring. But there should be so I'm not saying that we literally take the limit. I'm saying we have to do some weird operation on this to get some derivation.
Yeah.
And that operation, I know what the operation is in the case of k of x. And I can tell you the operation. It takes in... So I'm given algebra homomorphism, right?
Yep.
Then I see... And then what I do is I see what the algebra and what, like, for phi of x is. Because that's what all matters. That's what is like the governing thing for the algebra homomorphism. And let's say it's p of x. Then I create a new algebra homomorphism that takes x to x plus p of x epsilon.
Yep.
And so, since I defined what this is on x, I've defined it on the entire algebra. And so this is a new algebra homomorphism. And then, what I do is I define a derivation. So I'm going to so that delta. So I'm going to define delta acting on a function q of x to be. Let's see if I can reproduce this. The limit as epsilon goes to 0 of 1 over epsilon times phi of q of x minus q of x. Yeah. And this will give me p of x times dq by dx. Like I've proved this works. And
but you mean for k equals r?
No. Here I'm okay. So I'm saying the limit goes to 0, but I'm not really taking any limits because this is an algebra. I'm saying is I essentially expand this out, and so since phi x has this epsilon term, it's gonna have like other terms because q of x can be degree 2, degree 3, and I take epsilon squared to be 0. I take it to be nilpotent, and so when I expand this, the only thing I have in the numerator are of terms of order epsilon, because all the higher order terms become epsilon, and the 0th order term is just q of x by this, because phi of q of x is essentially the zeroth order term is q of x, and so q of x minus q of x cancels out. So this kind of looks like a Lie derivative of some sort, and I do get p of x times dq of x. So if I start from an algebra,
I need to understand what you mean by this. So I need to understand what you mean by this.
I'll show like a concrete example.
Yeah.
Right. Okay. So let's take p of x to be a thing that determines like the algebra homomorphism. Then I construct a new algebra homomorphism that sends x to x plus p of x times, like, let's put this as epsilon, because I'm gonna take limits. And so let's say this thing, now let's say this thing acts on x. So so I construct this algebra homomorphism, and let's say this acts on x. And so this is 1 epsilon phi of x minus x. And I know what phi tilde of x is. It's x plus p of x epsilon minus x. And so epsilon crosses out epsilon, I get p of x. Times 1.
Sure.
Now let's say I act on x squared. That gives me 1 over epsilon times phi of x squared minus x squared. Now phi is an algebra homomorphism, phi tilde. And so I know what phi tilde of x is, so I know what phi tilde of x squared is. It's phi tilde of x squared. Phi tilde of x is x plus p of x times epsilon. So it's x plus p of x epsilon squared minus x squared. So this is 1 epsilon times x squared plus p of x squared epsilon squared plus 2x p of x epsilon a squared b squared plus 2ab minus x squared. This cancels. Epsilon squared is 0 because it's a nilpotent.
But why you don't need to you don't need to invoke nilpotency in some sense, right? You can just, when you have 1 over epsilon outside, so that's telling you that there's a
I mean I can expand this and take epsilon to be 0, but like I'm not formally defining what a limit is in this aspect.
Well, I mean, you could. What I'm saying is that in this particular case, you could, because you're not taking
in the q of x case, I just set it to 0 after I expanded.
Exactly. Yeah.
But in like arbitrary algebras, is not clear. So, but like sure, like you're right. In this algebra, I can set it to 0. So I get p of x squared epsilon plus 2x p of x. So so if then I set epsilon to 0, so this vanishes, and so I'm left with this. So that's p of x times 2 of x, 2x, sorry.
Yeah.
So essentially, it's not hard to say that this is just this.
Yeah.
So I started with an algebra homomorphism phi. I constructed a new algebra homomorphism that sends x to x plus whatever phi sends x to, adjoined with epsilon. And then I construct this algebra, this thing, which is a derivation, and it turns out to be this.
Yeah. I mean,
so it's like, yeah, you were saying?
No, I was just going to say that this looks very similar to. I mean, in a way, if you replace k by r, for example, right, then I mean this is a fairly trivial result where you have any derivation. Sorry, there's a lot of noise in your background. I can't even hear.
I'll mute my.
So there's so this is a standard result where you have the fact that all derivations are infinitesimal and counterparts of sort of whole morphisms, right? So if you want to see it this way, in a particular case of R, any displacements. So in this case, something that takes your variable to a plus a finite amount, that's gonna, for a finite x, that's gonna correspond to some sort of linear map, and so you can always sort of take the derivative of that and find the derivation, right? So I believe what is happening here is that you have correctly identified this general construction that might work in principle, as long as there is a notion of there's a way to algebraically implement the notion of limit, which might well be that game of nilpotency or higher power trimming in some sense, right? You need some kind of trimming or some kind of convergence, etc. So yeah, and it basically gives you that. But it's still unclear to me. This looks very good, and I guess it's a matter of so knowing that all weighted derivations actually amount to an algebra homomorphism for the weights not zero, right? This is somehow kind of a bit of a mind-blowing result. It's not. It doesn't seem very intuitive at first that this is going to be the case.
Right. I have never seen someone or like in the literature say that there's a 1-1 correspondence. So even like for nice algebras, between algebra homomorphisms and normal zero derivations.
Yeah.
I've never seen anyone say that.
No.
I've just seen them prove that these are the set of derivations, and it just happens to correspond to the algebra homomorphisms as we saw in these two cases. And K of x1 xn, it also obviously works. And W derivations gives us a way, I feel, to go from an algebra homomorphism to a derivation. You basically modify the derivation by a little bit and let it go to zero. And I think there must be a functorial correspondence.
I think what's missing, the reason why you haven't seen that that correspondence, I think geometry gives us some sort of testing grounds for this general result, or plausible result, which is that it's essentially some kind of exponential map, right? This is the question of derivations are essentially infinitesimal deformations, right, to your geometry. So you look at a point and you say, okay, how can I flow away from this point, right? So in the infinitesimal description of that, infinitesimal here meaning in an arbitrarily small neighborhood of your point of interest, right? The question of how you flow out of that point in that neighborhood, that's a diffeomorphism case, right? It's you're speaking of whole diffeomorphisms of that sort of neighborhood, right? But it so happens that if you look at those that push away in your point somewhere near, because they are sort of connected to the identity, you could obviously have diffeomorphisms that are not connected to the identity, but if you're looking at particularly those, then there's going to be a one-to-one correspondence up to a factor, right? And the factor here is this idea that you're taking a limit, and you're actually looking at a class, as you saw that for each W there's a class of things that you end up getting, right? So, but that's that's not the same as saying that you take your algebra as a whole and and then you have a one-to-one correspondence. That's true for some algebras, and that's fine. But
yeah, it's true for those algebras in which the notion of a limit is well defined.
Is it that might be a way to put it? Yeah, that's a more analytical way of describing it.
Yeah, I mean, even if we can show, and I think that's going to be a major result, even if we can show, or like we can first define, like we can take inspiration for how we're taking like these limits of going from an algebra homomorphism to a derivation. And then if we try to like figure out what's important and try to generalize it, and we are able to do it for a few algebras, I think that's a good thing, right? I think there's a lot of like rich mathematical things over here.
Yeah. Well, I wouldn't. Yeah. I mean, I agree that there's potential there, but I would also try to, and especially for today's live stream, that is a shorter one, try to circle back to our motivating instance, right? Which is finite difference operators, and how finite difference operators happen to be weight one derivations, right? So something that might be very interesting to think about for the next 5 minutes or 10 minutes of the live stream before we have to call it off until next week is how would this result ring in the context of finite difference operators on discrete models of geometry, right? So let me set up the question. So basically, according to your construction, there seems to be a one-to-one correspondence between weighted derivations and algebra homomorphisms over the same derivation, over the same algebra, right? So this correspondence would mean that if we choose some discrete graphic manifold, meaning some finite set of vertices with a graphic structure on top that we're interpreting as geometric data, the weighted derivations here can be understood as vector fields in our discrete manifold, which are essentially assignments of directed edges to each vertex, right? And then if you have such an assignment and you have a function, you automatically have a finite difference operator, and the set of all those satisfy the one derivation rule, right? The one Leibniz rule. So here, the point will be, what is the induced algebra homomorphism from a vector field, right? So effectively, by assigning directed edges to each vertex of your graph, you should be able to see a single algebra homomorphism, right? So it's interesting to try to understand what this means in that context, because that is a very striking result in the face of it.
Sure. I haven't like gone into the geometry yet, but sure, we can think about that. Also, I might have to mention, like I did like significantly more stuff other than just finding a closed operation on W derivations.
So maybe do a review, because I think we might get lost in the details, because the details will be good for longer streams where we actually do the research. So just maybe overview the results and we can see.
Okay. If f is a weighted derivation of weight W1 and G is a weighted derivation of W2 weight, then this is a weighted derivation of weight W1 times W2.
Okay, that's very interesting.
This can be proven. Then there are like some corollaries which are probably useless, but like they look nice. Like if you have one derivation and the characteristic of the field is 2, then this is a one derivation as well. And so the one thing I might mention for all the people who are very, very into algebra is that this phi minus identity, like when I saw this, I immediately thought Jacobson radical, because the theorem says, like in algebra, that if you have any algebra, then an element is inside the Jacobson radical if this is a unit for all I, and the Jacobson radical is essentially the intersection of all the maximum ideas in an algebra. And so
And what is a unit in an endomorphism ring? It is essentially an isomorphism, right? Because you can invert it on both sides. And so a corollary of this theorem is that if the algebra homomorphism is in the Jacobson radical, then the weighted derivation is an isomorphism. It's like a vector space isomorphism. It's a linear map that sends the basis to a basis. So it's not like a very useful corollary, but like it is like an interesting mathematical task to just mentioning that. Now comes the more interesting stuff. If you guys remember last time, Carlos, you mentioned that I mean the idempotent idea seemed interesting. So there's this construction called the dual number construction, which like takes in a polynomial ring and mods out by this.
Yep.
Where essentially t squared becomes 0. So in other words, it's nilpotent. What I've done here is I've essentially taken this. So t squared becomes w potent. I've defined what w potent means. So when w is 1, it reduces to the notion of idempotent. And so here I define the dual number construction for an algebra, but with a weight w instead of weight 0, and I try to generalize it. So it has this notion of multiplication, which reduces to the ordinary notion of multiplication where w is equal to 0. In other words, it reduces to the semi-direct product. And so you can prove some basic things about them. And okay, so now comes like the nice theorems that hold in the case of normal zero derivation, is that if I have an algebra A and another algebra M, okay, so in this case M is like a bimodule, but that's not really relevant to our discussion. Like it has more details and stuff, so I'm gonna just say it's an algebra. Then the set of all derivations, as you correctly point out, are the set of all infinitesimal automorphisms that send A to A plus F8 times epsilon and ME to M epsilon to M epsilon. And you can prove this is a calculation intensive result. And the good thing is it holds true for W derivations as well. If I have any algebra homomorphism, then this map, which sends A to the weighted derivation instead of the normal derivation, times epsilon, and A prime epsilon to the algebra homomorphism that induced the weighted derivation, then I get an algebra homomorphism from the dual numbers to the dual numbers. And it has a very nice property that if the original homomorphism is an isomorphism, then this will also be an isomorphism, and it also holds the opposite way. So this is an isomorphism if and only if this is an isomorphism. And also there are like nice algebraic properties that if I take the composition of two of these operators of algebra homomorphisms and then try to find the induced algebra homomorphism on the dual number construction with weight W, then it obeys like this nice group property, the group homomorphism property. And so the corollary is that this weighted morphism is a injective group homomorphism. And so yeah, this is the stuff that I did to like here. Then in the case of normal derivations, they try to say that the dual number construction is the most specific type of an extension of an algebra. So this is viewed as an extension of A, because all the terms of this are of this form, right? And so this is like some weird extension of the algebra A. And so I try to generalize it with the case of W extensions. And over here, the deformation theory we talked about comes into play. And so I tried to like prove a few like nice results about extensions with weight W0 and try to extend it to W is equal to any W. And it didn't turn out to work out, but like I got some very nice properties. I didn't get like any deformation theory results, but it seemed to hold like some nice equations, and I haven't figured out how to understand them, but like they do look nice and they have a nice pattern to them. So yeah, that was the update on my side.
Oh, that looks excellent, Uti. That's a very promising prospect. Now, the one thing I would say is this algebraically, this is kind of getting to the point where we probably need to focus on specific theorems or specific results that will be relevant to the project, because this looks like something that can definitely sort of grow on its own and become a future paper or something beyond the infrageometry project. So it's not that I want to cut your your dreaming about these algebras and so on, but because I like it myself a lot, and I mean I love just losing myself in computations and just checking nice things. I mean, that's why I like algebra, because you can have nice things in algebra, unlike other fields of mathematics, right? So, but I think it's important that we keep in focus what these algebraic objects are good for in our context. So as next steps, it would be important to know what, particularly this construction, and this is something that we'll check tomorrow. What is the implication for the discrete geometric model interpretation of weighted derivations, right? Because it's actually uncommon and this is something that actually you encounter once you try to work with differential geometry a bit too much, and you try to go beyond the standard the standard beatings of differential geometry. You actually realize that almost nowhere algebra morphisms are brought up. So it's very rare to find an abstract multiplicative map between algebraic counterparts of manifolds. So, for example, a ring homomorphism between two manifolds. So those are always brought up in the context of if you have a smooth map between manifolds, then you get an induced pullback of the rings, and that's or the commutative algebras, and that's a valid multiplicative map. But general multiplicative maps, but those are not necessarily all the multiplicative maps, right? So general multiplicative maps between commutative algebras of associative of functions, or modules of sections of the tangent bundle, or some vector bundles, or things like that, right? Your algebraic counterparts of the geometry, those are almost never brought up, and they are very rarely used. The reason being, I think, because they probably contain a lot of gibberish information. Like, there might be a lot of well-defined maps between these spaces that basically break. So that algebraically behave well, but geometrically make no sense, right? So they break sort of the topology, or they break the geometry in some sense, right? So this is kind of the subtlety of geometry. So I completely... And that might be why because I am a geometer by training, basically, that I'm finding these results a little bit counterintuitive. That when I'm thinking, how could it be that I can actually map between homomorphisms and derivations, where in fact it might be that that seems that there's something not quite right in that correspondence, or you're looking at or that homomorphisms in fact were a much trivial kind of set of mappings in that context anyway. So to focus things back to the problem and to wrap up the stream today, because I apologize everyone who is following or watching the recording. I've been moving to a new flat. You can see there's unmounted stuff in the background. It's a new place, so empty walls, empty ceiling, and everything. So
it looks good, to be honest.
And I mean, it's good. I mean, you can see the kitchen is a nice flat, but it's empty. As you can see, I'm sitting in a single chair here. So it's a nice place, but I just had to scramble and get everything together. So hopefully by next week I'll be fully settled and have all my stuff here and an office to work in and so on. But circling back to the original motivation, also Jonathan has been very busy with Gravitas projects in the US, and we've been sort of detached a little bit. And next week we have the Wolfram Technology Conference. So all in all, this algebra development is amazing. I have to say, it's really eye-opening to see all these constructions, and we're gonna make good use of them. But it will be good to as much as you can carry on exploring. I quite like this idea of the W potent sort of constructions. I think that these are interesting, and they I think those are very close to the philosophy, or to the sort of kind of flavor of discrete geometry that we want, right? And yeah, so for next time, we hopefully will have some extra results. I'll work on the geometry side. Unfortunately, I didn't have much time to do the geometry this time, but I've been thinking about, as I said, parallel transport and what this tangent structure, this discrete tangent structure means. Now that we have these algebraic results, I actually have some explicit questions to sort of ask the geometry, because we have to see how these results translate. But all in all, I wanted to congratulate you publicly, because this is really good work. And so we can stay in touch for next week, and everyone do look forward to our institute relaunch event at some point, because at this moment in time, we are again with a bit of a internal restructuring, and this is taking a while because processes are a bit delayed internally. But other than that, great science is being done, and we are all quite excited. And as you can see, the moment you give some of our visiting fellows like Uti some space, they fly into the beautiful algebraic territory. So great to see that.
Sure. I must say I am excited to look at the geometry aspect, because, as you said, it's we're doing this because of geometry. So yes, the link between algebra and geometry is there. In fact, the reason I wanted to see the correspondence between homomorphisms and derivations is that we are essentially taking a limit, and so if there exists a functorial correspondence between homomorphisms and derivations, we should be able to that's what our original goal of the Infrageometry project was, right? To create correspondences between discrete manifolds and then making sure that they are preserved on a limit.
Exactly.
Yeah.
That's very good.
So geometry is the next step.
So as a very concrete comment after these very general, nice sounding words, would be for you to maybe explore the case of R2 derivations, so the derivations of the plane. And try to match that with so essentially look at the proof for y derivations are p plus q, with partial x, partial y, which, I mean, you can do this algebraically, but the geometry, I mean, if you only work with finite polynomials, you can do this algebraically by defining partial x, partial y as the linear maps that map x to 1 and x to 0, or y to 1 and y to 0, respectively, right? So then you have to make some argument to show that there are no more maps than those, and then you basically prove it from there. But in general, you will see that when you don't have the nice finite polynomial setting, you have to use some kind of geometry, right? You have to use, you need sort of something to limit the algebra. The algebra is very wild on its own. When you only impose algebraic conditions on objects, things are very wild. So you need something like saying, no, these are only finite polynomials, which is essentially sort of cutting off your things so they don't run wild. Or you're saying these things are continuous, so that you can wrap things with limits, and you can always, bring things down. Or you even further impose smoothness or things like that to further constrain. So that's kind of the intuition behind geometry, is that the algebra in its own can be very wild, and when you have a geometric shell or a geometric constraint, things become much more tame, and you get interesting algebraic phenomena within those bounds of constraint. But anyway, that'll be next steps.
Sure. Yeah. Next step.
All right, Udi, great to see you. Good work, and we'll see you next time, everyone. Goodbye.